Hi everyone, and welcome to this new video about three-phase power circuits. In this example number 2, we will consider a Y-delta connected system. So the source is in the Y configuration, the phase voltages, and the load will be in the delta configuration. So we have again the following situation. The following data is given for this Y-delta system. It is operated in 50 Hz. The phase voltages have amplitude of 600 volts, each of them. And the phases are 0 degrees, 120 degrees, and minus 120 degrees. We have discussed this in detail in example number 1 also. And the loads are all the same, so ZA, ZB, and ZC are all the same, actually shown here. So and it's a series combination of the resistor and the reactance of the inductor. So we have the resistance of 80 ohms, and we have an inductor of 191 millihenries. Okay, those are the given. We would like to calculate the following: the line voltages, VL1, VL2, VL3, and we would like to determine the load voltages, so the volts across each load. And we would like to determine the load currents, so what's the current flowing through each load, and we would like to know the line currents, IL1, IL2, and IL3. And of course the phase currents finally, which is actually the current supplied by each phase voltage. Now, before we move on with the calculation, let's start first determining the impedances, because we know the resistance, but we don't know the reactance of the inductor. So let's first do that. So the loads. Now we know we have the X of L, the reactance of the inductor, which is omega times L, and that will give us omega is 2 pi times the 50 Hertz, which is already given, and times 0.191, which is given, and it will be 60 ohms, very close to 60 ohms. And then we have the following, that the ZA, which is also the same as ZB, and which is also same as ZC, will be 80, and then 60 ohms. Now, if you convert this to the rectangle, the polar notation, it will be 100 phase 37 degrees in ohms. Okay, now we have the required expression for the loads, ZA, ZB, and ZC, and we have an inductive system, so actually we can move on with the calculation for question A. So what do we have for question A? We have the line voltages. Okay, now we have to be very careful. The definition in this case for this circuit, that the line voltages will be calculated in a clockwise direction. So what I mean by that is the following. For VL1, this one, I will use VB minus VA. So I will use first this node and then moving in the clockwise direction to the following node. And for the other one, I will do the same. For example, for VL2, I will first use VA and then minus VC. So that's actually in the clockwise direction. So what I do now next is the following. VL1, which is what we said before, VB minus VA. Now we already know the phases and the amplitudes, so the polar notation of these phase voltages, so that will be 600 phase 120 degrees minus again 600 and 0 degrees. Now if you again calculate this by converting each of these terms to the rectangular expression, because then you can easily subtract them or add them together. This will result in, I will leave the details in this example out, so this will result in square root of 3 times 600, or you can also write it down as 600 times square root of 3, and this will result in a phase of 150 degrees. Again, is in volts. So these are given in detail in the example number 1, so I will leave these details out of this example. So we have the VL2, exactly the same procedure, because we are going clockwise. We look at this node and then going actually to node C, and this is actually for VL2, as you can see, but this is also node C. So what we have is VA minus VC, which will be a 600 phase of 0 degrees minus 600 volts phase of minus 120 degrees, and this will result in again exactly the same expression for the amplitude, 600 times square root of 3, so that's exact same, but the phase will be 30 degrees. And we have discussed this also. You can see that the phase will drop in each step with 120 degrees. So we will lose 120 degrees, so you will decrease the phase, but you will have the exact same expression for your amplitudes, for your line voltages. So the final one, line voltage 3. What do we line voltage 3? This is this one, which is VC minus VB. So again, in the clockwise direction. So what we have is the VC minus VB. I will write down the expressions in the polar notation. So what we have is the 600 volts minus 120 degrees, and then minus 600 volts, and in phase of plus 120 degrees. If you again do the math by converting the polar notation to rectangular notation and add them up and again convert to the polar notation, you'll have again the same expression for the amplitude, but the phase will be, as we discussed earlier, will again be decreased by 120 degrees, which will be minus 90 degrees in this case. So what we have is again a reduction in the phase, but the amplitude will be multiplied by a square root of 3. Okay, that's actually for the line voltages for this system. What is all about the load voltages? Load voltages. Okay, so load voltages, because with the orientation, the polarity is from B to A and from A to C and from C to B, we have also the exact orientation for the load. So if I now use a red color, so if I now move from point B to point A, this will be actually for this load, I have the following. I have the plus at this side and a minus at this side, and the voltage we are considering is actually VZ of A. So that's actually the voltage what we like to determine, but this is exactly the same voltage as VL1. So I can say the load voltage for impedance ZA is exactly the same as line voltage 1, because it's just in parallel. And we already calculated that, so that's actually 600 phase 3, I mean 600 times square root of 3, and then phase 150 degrees. Okay, that's actually for the first one. Let's move to the second one for the voltage across the impedance ZB, which is this one. And you know already that the current is flowing from this point, from this node to that node. So actually I need a plus sign here and a minus sign there. Let me check this, if this is correct, because this point is A and we are going in a clockwise direction and we are going to point C. So it is point A minus point C. So voltage at point A minus voltage at point C, and we see that also in the expression for the voltage, and this will be VZ of B. And again, you see that this is just the voltage VL2, so the line voltage 2. Okay, so we can just copy the VL2 we already calculated, which is 600 times square root of 3 and then phase of 30 degrees. That's actually for this one, and for the voltage, load voltage at for load Z of C, again, this is the plus, this is the minus due to the orientation of the current. Let's check me that, because let's check the orientation also. This is the voltage at point C, and we have to go to move to point B because of the clockwise direction, and this is point C and this is point B, and it's correct. So what we can say is, again, this is VL3. So we can say it's VL3. So let me write it down in a bit clearly. So this V of ZC is equal to VL3, which is exactly 600 square root of 3 and the phase of minus 90 degrees. And it's all done for question B. Now we have to move to load currents. Actually, this is very simple. Since we know, using Ohm's law, we know the impedances for each load. It's already given. We have calculated this here in the first step. And we know the line voltages and also the load voltages. So we can say the following. Let's move up. So we can say for question C, load current can say the following: the I z of a, so I z of a will be v z of a divided by z of a, and it's exactly the same as the line voltage. So this will be 600 square root of 3 in the phase of 150, and I will use the polar notation of the ZA, which is 100 phase 37, and this will result in 6 amperes, and then phase of, you do the following, we already know that, because you divide the amplitudes and you will subtract the phases, so you will have 600 square root of 3 divided by 100, and you will have 150 degrees minus 37 degrees. So that's actually the expression what we need. So we have the 6 and the square root of 3, that will result in 113 degrees in amperes. So actually for this, let's move to the IZ of B, which is VZ of B divided by Z of B, which is again 600 square root of 3 phase, this time 30 degrees. We have this here or here, it's exactly the same. So divided by, again, 100, and then phase of 37 degrees. And this will result again in the same expression for the amplitude, but the phase will be minus 7, and again in amperes. Now we are almost done, the last one, the final one, and I will move a little bit to the left. So I have the IZ of C, which will be VO Z of C divided by the impedance ZC, which is 600 square root of 3, and then phase of minus 90 degrees, which is shown here, and divided by the impedance we have already calculated, which is 100 phase of 37 degrees. And if you do the math again here, you have square root of 3 times 6 and the phase of minus 127 degrees. So what you recognize here is also the phases will drop also by 120 degrees. So each step I will lose 120 degrees. Okay, these are the load voltages, I mean the load currents, IZ of A, IZ of B, let me zoom out, Z of A, IZ of B, and IZ of C. Now I'll now move to the fourth equation, question, line currents. Okay, what are the line currents? So let me write it down. In line currents. Okay, the IL1, first write it down, IL1, which is, if you look at the circuit, IL1 is this current, which is actually this current minus this current. You can also consider that in a different way. This current, IZ of A, plus IL1 must produce IZ of B. So this is actually the production of these two currents. So I will have the IZB minus IZA is IL1. So that's actually the expression for IL1. So again, I have IZB minus IZ of A. And if you use the expressions we have already calculated here, so this is B for A, again the same amplitude but different phases, so 6 square root of 3 phase of minus 7 degrees, and you will have minus 6 times square root of 3 and then phase of 130 degrees, and you will get, again doing the math with converting this to the rectangular representation, you will have the expression of 18 and phase minus 37 degrees in amperes. So what you actually have is the following. You multiply this by square root of 3 and you will get this. That's actually the analysis here. Maybe I will do that. It's maybe better, so that you can see where is the square root of 3 in this example. So I will unpack this using the rectangular, transforming a polar notation to rectangular form. So let's do that. So 6 square root of 3, and I will use the cosine. This is actually a familiar equation we know from the video of phasors and complex numbers, and then plus j sine of minus 70 degrees, and that's for the first part. And the second part I will do the similar one, but using the cosine of 113 degrees, and then j sine of 113 degrees. Again, this is IL1. So if I now combine the real parts, so I have the real part here and I have the real part there, of course a minus sign, and I have the imaginary part here and imaginary part there, and of course a minus sign here. So let's first, and I move of course the 6 times square root of 3 outside. That's also possible. Or you can do the following: you can calculate this, and you fill it here, and you calculate this and this. You can fill it in the brackets, and you can add the real parts of. That's also possible. So let's maybe do the second one. So this one will be 0.993, and this will be minus j 0.122. This for the first one, and minus 6 square root of 3, and you will calculate the second one. This will be minus 0.391, and then plus j 0.921. Now you have to add the real parts and imaginary parts, and I know they have all the amplitude of 6 times square root of 3, so I will take that out. So I will have 6 times square root of 3, and I will add this to this, but I have a minus sign, so I will have this one, so I will have the following: 0.993 plus 0.391. That's actually for the real part, and for the imaginary part I have the j, which is of course the minus sign here, because all of them are minus. You see that there's a minus sign for this one and a minus sign for that one, so we have the minus 0.122, and then minus the 0.921. So minus or plus, if you take that in brackets, so we have the 0.900 of parentheses. So I have the following expression, and if you simplify this, just have the only one real part and one imaginary part, what you get is 1.384 minus j 1.043. Now if you now convert this rectangular expression, the polar expression, and calculate the amplitude, of course, and the phase, you will have the following. So I will do that here. So 6 square root of 3 is still in place, and the amplitude of this one is the real part squared plus the imaginary part squared, and then take the square root of that. That's the already known formula. So I will do that here step by step, so that you can see why it is square root of 3 again. Again, I will use a minus sign here to emphasize it is a minus, and that will give us also the phase arctangent of the imaginary part, minus 1.043 divided by 1.384. Now if you do the math, and if you have the exact expressions for these values, you will have actually 6 times square root of 3 times square root of 3. So this expression, if you do the math exactly, must be square root of 3. So this will result in a phase of, for this one, you will have the phase of minus 37. And this will result, because it's square root of 3 times square root of 3, this will result in just 3. So you will have 6 times 3, this will be 18. So this is IL1. So as you can see, I have done this in quite a few steps to express why this is actually from the polar notation to the rectangular notation, and going again to the polar notation, you will have this expression. So I will do it for IL1 and for IL2 and IL3 in a much faster form. So what you can see is this expression, and this procedure will be also followed for IL1 IL2 and IL3. So I will a little bit zoom out and I will go to the right side to go for the next one is the IL2. And let's look at IL2, what the line current 2. A little bit zooming in. So what we have is the following. IL2 is this one, which is actually this current IZ of A minus this. So IZ of A minus IZ of C. So that's actually for the second line current. So let's move on. Okay, this is actually here. So IZ of A, set IZ of A minus IZ of C. Okay, that means again in the notation of the IZ of A is actually here. So you will take this and you will do minus this one, this expression, and then you're actually done. So this is 6 times square root of 3 phase 130 minus again 6 square root of 3 phase minus 127 degrees. Again, do the math with converting the polar notation to rectangular notation and everything. You group them, real parts and imaginary parts, and simplify the expression. You will have 18 phase 83 degrees. In a similar way, IL3, which is, so let's look at the circuit again for IL3. This one. This current flowing this branch and coming to this node will be, of course, IZ of C minus IZ of B. So C minus B actually. So let's look at this also. C. So IL3 will be IZ of C minus IZ of B, and all of them are actually expressed here. So we can say the same for this calculation. 6 times the square root of 3 phase of minus 127 degrees minus 6 times the square root of 3 phase of minus 7 degrees. So I will have this, and again using the rectangular and the polar representation transformation from one to the other form, you will have IL3 is equal to 18 phase 203 degrees. Okay, of course you can convert this to a minus sign by subtracting 360 degrees, and you will have exactly 18 amperes and a minus 157 degrees. I will actually have exactly the same meaning with that. Okay, that's actually for the line currents. So let's look at the next one, which is, we have now determined question T, which are the line currents. Now the phase currents. What are the phase currents? Now let's look at it carefully. These are the phase currents, so I will make this clear in red. So this is the phase current I phase of B. This is the phase current for C, and this is the phase current for A. Now what you say is actually the following. The phase current for phase voltage A is line current L1, IL1, okay. And the same procedure for the phase current B will be IL2, and for phase current for source C, IP of C will be IL3. So actually this is very simple, because it is a series connection. You already know the phase currents are exactly the same as the line current. So the final one will be very simple. So I will have the following. So E phase currents, let's also calculate that. So let's start with the phase A. Phase A will be IL1, which is 18 phase minus 37 degrees. Now let's move to phase B, which is IL2, 2 is already calculated here in equation D, which is 18 phase 33. So I mean 83. So we have this one, and 83, 18 amperes, and a phase orientation of 83. And the last one is the phase current for C, which will be IL3. We have seen it in the circuit, and it will be this one, 18 amperes, phase 203 or minus 157, what you prefer. I will do also the minus sign, so I will have the following expression for the phase current. So that's actually the whole example, considering the 5 unknowns again, or set of unknowns, because we have the set of line voltages, load current, line current, and phase current. So we have a lot of questions actually. It looks like 5 questions, but we have a lot of questions. So we have discussed this in detail. In this example, we have also discussed a different load, which is not pure ohmic, so it's not resistive. We have an inductive load. So we have also considered to determine the impedance before we move on with the actual questions from A to E. All right, that's actually for this example number 2, about Y delta or star delta connected system. In example number 3 and also the other examples, we will consider different configuration of power 3-phase power circuits. So I will see you next time, and don't forget to share and like, and take care.